Welcome to another lecture on the different facets of structures of chemical compounds. Today's an introduction to bonding. Now, one little aside, when I was talking about Schrodinger's equation in the last section, I allowed the students' nickname for the expression for the wave characteristics. They call it the cactus. Its actual name is psi, PSI, and it's a Greek symbol. It's up here on the corner so you can spot it. I'm sure I had it in the last one. Okay, today we're going to cover bonding. There's three primarily easily illustrated types. They are polar, covalent, and ionic. Now, polar, which you're quite familiar with for water and ammonia, and even carbon dioxide, is based entirely on the repulsivity of electrons, pairs primarily, and their dislike for one another, since there's rarely lone pairs in compounds, non-existent almost. Now, water is polar because the hydrogens are forced, even bonded, away from the unbonded pairs at the bottom of the molecule. Thus, it has a positive side and a negative side. Now, I've covered that ad nauseum because of the unusual characteristics of polarity. But others that you don't think about is ammonia, for instance, which has a really unusual shape, and carbon dioxide, which is linear, because the carbon has four possible electrons for bonding, and the oxygen has two. Thus, the double bond, as we say, for carbon dioxide. Now, covalent bonds are equal distance, and the breakage energy is quite high. For instance, methane is the classic. Methane is one of the largest providers of energy for mankind, and it is CH4. Now, the deployment of the hydrogens is equal distance apart, getting as far away from each other as they can, even in paired conditions. The electrons, again, don't like each other much. Now, breaking this up is surprisingly high energy-wise at 413 kilojoules per mole, and a mole of methane is 16 grams for Pete's sakes. It's a very small quantity, mass-wise. And that's the reason we use it. It produces a whole lot of energy for a very small mass. And that's an example of the covalent bonding. Now, ionic bonding generally refers to the use of hydrogen and halogens and a variety of periodic groups from left to right. Need to know primarily how many electrons are in the outermost shell. And for ionic bonding, you generally have 6 or 7 in the outermost shell combined with a 1 or a 2. That pretty much is the extent of ionic bonding. The size of the ions increase down the periodic table and left to right. And that's understandable because the atomic masses increase in that same manner. Crystals form, let's see, I was going to show first how that worked. Ionic, say you got hydrogen, lithium, and fluorine. Lithium's +1, hydrogen is +1, fluorine's a -1. And hydrogen fluoride and lithium fluoride are two compounds that would be formed from this. Calcium is a +2, column 2 2 valence electrons, and potassium is a column 1 again. And if they mix with oxygen in compound form, you got calcium oxide and potassium oxide. Now, the crystalline forms of some of these generally form in layers, interspersed layers. Now, the decomposition of these is really large, from, breaking apart table salt. It takes a tremendous amount of energy to disrupt the sodium chloride bonding. The highest of them all is magnesium oxide, which takes 3,925 kilojoules per mole. Wow, that's smelting the energy almost. It's really, really quite large. Next is Lewis structure. Now, there's rules for Lewis structure that I'll cover in a minute, but I start with the illustrations. For instance, the cyanide ion, Cn minus, you add the valence electrons. Carbon has 4, nitrogen has 5. Add them together, plus the extra electron above, you get 10 electrons. So you have to put together a structure which bonds the carbon and nitrogen together with a minimal number of bonding electrons, and still provides a balance in the structure of the molecule. Thus, you have a triple bond between carbon and nitrogen. I have to look at that again. And a single electron, I've got it's 2 electrons on one side, which would give it to 4. So do a little erasure here, because carbon only has 4. And that'll give you 6, 7, 8. Oh, wait a minute. Forgot about our negative sign for the polyatom. That's the way you get away with having that extra electron in there. So I overthought it, so to speak. So there's your 10 electrons, 6, 2, 2, and that means, by definition, it is unbalanced, and because the carbon can only have 4 valence electrons, and it has 5 shown on the structure, and it must be accounted for. And the way you account it is you put -1 on the outside of the bracketed structure. 10 electrons. Okay, hydrogen cyanide, which is the next one on the list. Hydrogen has 1, carbon has 4, nitrogen has 5. That gives you your 10 electrons. And you can put your structure with hydrogen can only have 1 bond, and carbon can only have 4, and it's not a charged particle, so it must balance out. Hydrogen have 1, carbon has 1, and I have that shown as a single bond, but you guys have just started to mess with this stuff. Probably shouldn't be so blasé about it. Here you go. That shows you 2 electrons, 1 for the hydrogen, 1 for the carbon. And then the other 3 electrons that are available for the carbon are shown in the triple bond. And the nitrogen has this double bond on the paired, lone pairs on the outside. 10 electrons, hydrogen cyanide. Next one, which is always popular, is bleach. It is OCl minus. Now, oxygen has 6 electrons in the outermost shell. Chlorine has 7. And then you have 1 for the charge, which gives you a total of 14 electrons. Well, You can see the 6 illustrated up here, and 2, 4, 6, 8 illustrated for the chlorine. Well, the chlorine can only have 7, so you have to account for it with a -1 on the outside of the structure. All right, rules. Sum all the valence electrons up, add them up, just like I got through doing. Use pairs of electrons to form bonds of all the involved atoms in the structure. Just did that. Third, arrange electrons, duets for hydrogen and octets for the second row elements. And I just did that. Remember, hydrogen, you can only have 2 electrons. Now let's further validate that for something that you're familiar with, carbon dioxide. Now, oxygen can only have 6 electrons, 2, 4, 6. And it's double bonded with carbon, and carbon can only have 4, 2, 4. So that gives you 6 for the oxygen, 4 for the carbon, and 6 for the other oxygen, and illustrates quite accurately, as I've had further up the scale here, carbon dioxide. The way you do it is you put it together, and if it balances out by valence electrons, then you call it a valid structure. If it's not balanced, then it's not a valid structure. Now, I'm not going to spend time on this, but something you can read on is there are some exceptions to the octet rule, and there's something called resonance structures, which you have a shared resonance of electrons. This is fairly minor in practical application of this, and you can read through it and get a hang of what it's about. It does exist. You should read through it at least once, and it'll give you some ideas of the variation in the octet rule. Okay, next is what we call VSEPR, valence shell electron pair repulsion. And I added theory on it because that's part of the show. Valence shell electron pair repulsion. Learn VSEPR. You've got to know it. You'll have to memorize it. It's something that will become second nature for you. It's used for textbook descriptions, lecture descriptions, lab descriptions. VSEPR is very important. All right, rules for VSEPR. First rule is to draw the Lewis structure based on the material I gave you just previous. Second, count the pairs of electrons, arrange them to where they're minimally repulsed, balanced. That's what I called it, but minimally repulsed is what the actual verbiage from the theory. And I showed that in the examples prior. Third, determine the position of the atoms by the repulsivity of the electrons. They'll be balanced in one form or another. Now, they'll have structures that will have understandable names. Now, your carbon dioxide would be linear, straight line, held together by the double bonds. That's a linear structure. Determine the position of the atoms, I've already said. Name the molecular structure. All right. You got ammonia, NH3. Now, typically, you would think of that as a tetrahedral structure. But because a lone pair is by itself and not an atom, you have to give it a different idea. The bottom of it becomes a triangle, and we call it a trigonal pyramidal because it comes to a point to the pyramid. So it's trigonal pyramidal. Now, the next session, we're going through a lot of these structures and their names. Now, I'm not going to spend enormous amounts of time on this, but I'm going to introduce you to all the most significant structures. It's kind of fun. Um, Again, you got to have your textbook. You got to have the periodic table. Those are your keys to success. There's not a lot of math involved in this. This is more of more aesthetics. So all you art majors that are burdened with the thought of taking chemistry, you might really like this because you can make some neat structures that are actually valid for a variety of these compounds. But there's very little mathematics in structural chemistry. Now, there is further along when you're figuring out the energy of the structure formation, but that's generally not overly emphasized in a survey course. So I hope you enjoy this. This is an introduction to bonding.